Okay, we're going to take a look at exercise 1 from chapter 4.3. And they give us the derivative of the function in factored form. And they ask us to find the critical points of the original function. They ask us to find on what open intervals is our original function increasing and decreasing. And they ask us at what points, if any, does our function assume a local maximum and minimum values. So let's go ahead and start with part A. And we find the critical points where the derivative is either equal to 0 or undefined. Well, x times x minus 1 isn't undefined anywhere, but it does equal 0 at either x equals 0 or x minus 1 equals 0, which gives us 1. So right off the bat, and here we see the advantage of being given the derivative in factored form is it's very quickly we can find those critical values. This is one of the reasons, again, why so many derivatives were simplified to factored form earlier. We finally get to see the payoff for that here. And next we'll go to part B. And with part B, we're going to build our sign chart, and on our number line, we put in our critical values. And again, this is going to break up the sign chart into 3 regions. 2 points breaks it into 3 regions. If we had 3 points, it would break it into 4 regions. And we're also going to go ahead and list out our different factors here. So again, I like to do them in the order that they give me the zeros. So I'm going to put x first, I'm going to put x minus 1 second. Both of these are linear factors. Both of them have a positive slopes. So they are both going to take on negative values until they reach their 0, after which they're going to be positive. And once we have that, we can go ahead, take a look at our entire derivative all put back together here. And so in this first region, we have negative times negative, which gives us a positive value. In our second region, we have positive times negative. That gives us a negative value. In our third region, we have positive times positive. That gives us a positive value there. So in this region, since it's positive, our original function is going to be increasing. In this open interval, it's going to be decreasing. And in this interval, it's going to be increasing. And if we wanted to write that a little bit better here, so f is increasing on the interval from negative infinity up to 0, as well as the interval from 1 to positive infinity. F is decreasing on that middle interval from 0 to 1. So that takes care of part B for us. And now we'll take a look at part C. And for part C, we use the first derivative test for local extrema. And at x equals 0, we see that the derivative went from positive to negative. If it went from positive to negative, it was going up, got to x equals 0, and now it's going down. That's going to be a local maximum of our original function at x equals 1, we go from decreasing, heading downward, to increasing, heading upward. So going down to up, that's going to give us a value there. That's going to give our original function f a local minimum. Again, the reason in each of these cases, our derivative went from positive to negative for x equals 0, and our derivative went from negative to positive at x equals 1. And if you think about what the graph of this would like with these changes here, from negative infinity all the way up to x equals 0, our function was increasing until we get to x equals 0, and then it is decreasing until we get to x equals 1, and then it's increasing again. And with that behavior, we see that our local maximum and our local minimum, we kind of see why it doesn't appear that we have absolute minimums and maximums at these points.